Yeah, if you're joining right now, we're working on a couple of questions on TopPad. So please log into your TopPad account and start answering the questions. Okay, so let's see your responses. Yeah, that's right. So we measure the magnetic field using Tesla. Weber, we'll learn about it today, hopefully. That's to measure magnetic flux. Magnetic flux is different from magnetic field. Magnetic flux is how many number of magnetic field lines are crossing some kind particular area. So yes, for now, we only know about Tesla. So SI unit to measure magnetic field is Tesla. Okay, let's move on to the next question. Okay. Can you see the picture from your side? If not, this is the picture. Remember, like last class, we learned about like spreading iron powder around a magnet. So the iron powder get arranged itself in the pattern of magnetic field lines. So that's what this picture is. So it's asking the strongest part of a magnet. So it's asking like where the magnetic field strength is maximum, or the highest place of magnetic field strength is. Okay, what is the chat message about? Yeah, you can log out and come back, join again. Oh yeah, oh, I forgot he can't hear. Nicolo, yeah. So sorry, someone sent me a chat message saying he or she can't hear me. Then I replied like in voice. Thanks for replying, Destiny. Okay, so let's look at your responses. Yeah. So by looking at the distribution of iron powder, we can determine where the magnetic field is more strong. So over here, it's so much crowded with the magnetic powder, iron powder, and also over here it's crowded, right? And here it's kind of very slow motion of iron powder distribution. It's less magnetic field strength is there. So by the poles, it's more strong magnetic field. So if you want to see a strong magnetic field effect, then we need to go all the way closer to the poles. So yes, your answer is correct. So most of you are giving correct answer. Then D, the force field. Okay, so those who answered as answer D, you are confusing yourself. So force, field, those are two different things. So the force field, please read the question. The strongest part of a magnet is the force field. Where is it? It's asking about a location, right? So it can't be force field. I'm a little bit worried because I have 12 of you answered the force field. Is there anyone who would like to argue or comment on that? No? All right, so the question it's asking about a location. The strongest part of a magnet is. So the force field is not make sense. It's not a location or anything. Like, I don't know what it is. The force field. Okay, so why does each electron in an atom behave like a tiny magnet? So if you remember in the previous class, we learned about like how the permanent magnets get its magnetic properties. So the baseline is the movement of charged particles. So when there are charged particles that move around, it induces magnetic fields in materials. So the question is asking, why does each electron in an atom behave like a tiny magnet? Okay, let's look at your responses. Go back. You don't need to respond again because you already did. So the question is itself is addressing to electrons, right? So its answer is obvious because electron, the word electron is there. However, remember that the electrons are the moving particles. So electrons spins up and down inside the atom. So that's create magnetic properties. Then why not all materials get magnetized? That's a good question, right? So some materials just have its property, like they can arrange themselves to create these magnetic folds separated, but some materials does not. So ferromagnetic materials can be easily magnetized. Okay, so there are magnetic materials and non-magnetic. But if you think about a permanent magnet, it does have its own magnetic possibility of magnetizing itself. So in those permanent magnets, the electrons are spinning up and down. That's create the magnetic poles, giving a magnetic effect to these atoms. Okay, so this is a little tricky question. So when you answering it, read it, and if you can, draw two magnets, draw it on a paper, and draw the magnetic field lines around the two magnets, and then think about it. Okay, so if you place a small needle between the north pole of two bar magnets, okay, so for a second, forget about the first part about the small needle. Think about two bar magnets facing to each other, north pole to north pole. So draw two magnets on a paper and think about what's the direction of magnetic field lines. So draw the magnetic field lines around the two bar magnets, and then think that you're going to place a needle in between the two magnets. And it's asking, will the needle become magnetized? Yeah, you can take some time on this question.
Excuse me, the last question we just did was neither, correct?
Which one? The about the spinning of an electron?
Yes.
Answer is A.
Oh, because I put that in, it said that neither answer is correct, so I just thought I had got it wrong.
Did I have that answer in there, like a neither? I thought I had only two choices.
Yeah, but I picked the first one, that like the one correct, and it says no correct answer.
Oh, okay. So that's maybe I didn't select that then. Okay.
Yeah, that's what
The answer
mine
is A, the electron spinning. Okay, I'll go back to that question after I complete this one. And let's see what happens there. Okay, so I see all of you have answered. So let's check your responses. Oh, it's a quite variation here. But most of you got it correct. Okay, so it's asking, if you place a small needle between the north pole of two magnets, will the needle become magnetized? So here, this I don't know whether you can see my screen, not the screen, my video. If you can't, you can click on the speaker view, then you should be able to see my screen here. So you need to draw, I don't know whether it is mirror image the picture. So here what I draw is two magnets, North Pole and South Pole, and a North Pole and South Pole. Then I drew my magnetic field lines around the magnet. Okay, so we know that the magnetic field lines start from north and it's go toward the south. Now here, the magnetic, there are so many magnetic field lines compared to this area. However, there's another magnet with a north pole on that side. So all the magnetic field lines will get bended. They are not crossing each other. Like very similar to the electric field lines, it will get turn, and they are not crossing each other. Supermerge. They will be supermerged and turn in. So this area in the middle, it's an empty space. So there's no magnetic field over here. It's zero in the middle. So if you keep anything in there, you cannot get a magnetic effect. Okay, so I see like half of the class answered it incorrectly. So you need to think about this. But just in case, if I flip this magnet, if I keep the south pole on this side and north pole on the other side, then the north-south facing each other. So we have a strong magnetic fields over here before it's attached to each other. You know, like they're attracting to each other, but you can hardly hold the two magnets, making a strong magnetic field in the middle. That's if I keep north and south facing together. But in this question, it's north-north facing to each other. So in the middle, it's zero magnetic field. Okay. Now this idea can be used to send a charged beam through this center. So in the accelerator facilities that take using this concept. So if they wanted to send a charged beam like electron beam or a proton beam, then they will be sending through this center. Okay. Is it make sense? I don't know whether you were able to see my video with my the picture like this. Okay, so those who have answered incorrectly, think about it. Why does that happen? Or what is the direction of field lines and why the center magnetic field is zero? Now, if you want to magnetize something, you need a magnet and a metal pin or something like a needle pin. You can take the magnet and then just imagine this is a magnet. So if this is a needle, I need to rub the needle against the magnet like in one direction. So you can magnetize the tip of the needle. Okay. So by rubbing this way, you can magnetize it. That's one way of making it magnetized. But here it's asking like, if you keep the needle in between North Pole and North Pole, can you magnetize it? Okay, so let's look at the chat here. I think you prefer to send chats. Can you take a picture of your drawing and send it in the chat window? I don't know. I can try. Honestly, I can find another picture and send it to you later, okay? I can draw it on a... So field lines. So the field lines start from north and go towards south, right? So over here, I'm not good at drawing on the notepad. So it's curving around and turn around. Right? So the direction of magnetic field is starting from north and go towards south, right? So in this area, let me grab a different color. So this area, the magnetic field strength is 0. So in the middle. So it doesn't matter whether you keep something over there, there's no magnetic effect happens over here. Even though this area is more magnetized, if effect is there, all the magnetic field lines deflect at each other because there's no north pole, so they're repelling, right? So if you have, okay, I don't need any comments here. Okay, so this magnetic field line, oh sorry, it can't cross. The magnetic field lines will never cross. It's just supermerge, right? Turn. Okay, so there's 0 magnetic field strength over here. I stopped sharing, so we went back to the main room here. Okay, I still have Toppat open. Okay, all right. So please think about it and draw the field lines by hand so you can understand it better. Okay, so I'll keep moving to the next question. Remember, like in the last class, I used dots and cross. Then most of you answers incorrectly in the question. So I broke down the question into pieces. First, giving you an idea what does this represent. So, what does the following picture represent? So you see like a circle and a dot in the middle, and there are a whole bunch of those, right? So what does that represent? All right, so let's see your responses. Okay, again, half of the class got the correct answer, half did not. Oh, I like this one, a bunch of coaxial cable. That's true. Unless you have taken any physics class, right? So this is a really nice representation that we are using in not only in magnetism, but any place that you want to show direction of something. All right. So think about an arrow. You know what I mean? Like arrow we are using for the arch race, archery. I don't know whether I'm pronouncing it correctly that you can pick it. Arch race, like you shoot. So shooting games that you're using arch race. So in those ones, if you have an arrow, so when you have an arrow it's coming, yeah, if an arrow is coming towards you, you will see the tip of the arrow, right? So let's say this way. Okay, so let's say I have an, I need a bigger one. Why? It's not a stamp, I need an arrow. So let's say here's an arrow. Okay, so usually, this is the back of the arrow. This is the front of the arrow. So when an arrow coming towards you, and if you're looking from this side, so let's say you're observing it just standing up from this side. So your eye, believe or not, it is your, it is my eye. So here I'm looking at the arrow from this side. Okay, so this is, here's the observer's eye. So you're observing an arrow which is coming towards you, towards your eye. So what would you see? Will you see the whole arrow, or you just see this point that's coming towards you? You will be seeing a point, isn't? So you will see just a point coming towards you. So in our drawings, we draw it like this. So this side, we will see, if it is coming towards you, you will be seeing a dot coming towards you, right? And on the back of the arrow, like if you're observing it from this side, so you keep your eye on this side. So you're seeing an arrow going away from you, and you're observing it from the, this is my eye, okay? Don't confuse. Oh, why can't I draw it nicely? Okay, so this is the observer's eye, and you're observing an arrow that's going away from you. So you will be seeing the back of the arrow. So if you're familiar with arrows, it's kind of like this. So when you're observing it from this side, you will be seeing a something like a cross going away from you, right? So the symbol that we are using to indicate that something going away is this. Is that make sense? So this is a model to represent directions. So if it is going right or left, we can use just an indication, like you use the arrow indication, like, okay, here you go. It's going to the right, to the left. But if you're looking from another dimensions, like you turn and you see it coming towards you or away from you, it is another dimension, right? So you cannot draw it on a two-dimensional space. So you need to look at it in three-dimensionally, and this is the representation of directions in three dimension. In the third dimension, I guess. Okay. So in this one, these dots represent something coming towards you. So in the answer should be D, directed out of your screen at you. So you're looking at a computer screen, right? So it's coming towards you from the screen. That's why you see dots. And what about this? Uniform magnetic field. So uniform comes from this nice symmetric distribution. So you see, like on the top row and the bottom row, we have the same number of field lines, directions drawn. So it is not asymmetric, it's symmetrically drawn, right? So it is a uniform distribution, it's uniformly distributed. Okay, so the answer should be uniform magnetic field directed out of your screen at you. So can we use this representation to represent something else, like let's say current coming towards you, a wire that's connected and the current is coming towards you. Can we use the same representation? Actually, we can. But here I specifically mention its uniform magnetic field because we are learning about magnetic fields here. But it can use to represent the direction of anything. If you want to say it's coming towards you or going away from you, then you can use this dot representation or the cross representation. All right, so let's see whether you got it or not. What does this represent?
Hello?
Yeah. Yes, go ahead.
Hello?
Can you hear me?
Yeah, I just joined the call. My computer wasn't letting me join. I just wanted to let you know because I
Okay.
didn't know the
So we
attendance
are
yet.
working on a couple of top hat questions. I think we are in the 5th question now. So you
Okay, I'm
can
going to.
review those questions on top hat later. Okay. I didn't count the attendance yet, so you should
Okay.
with your credit, but I want you to review the questions later. Okay.
Okay, I'll do that right now.
Okay, I think almost all of you have answered, right? Yes. All right, so let's see. Give me 100%. Okay, so the correct answer is D. So still there are about 20 students who get messed up. So think about it, okay? So if you have any other, like if you want more help, you can stay after the class today and I'll help you out to see like why it is. Okay, why it is important? I'm not going to be a physics major, I'm going to be a nursing major. Why should I worry about this? Isn't that a good question? Actually, what we are doing here is giving you some kind of scientific background. So there are different models that we can use to represent things. So you should be able to understand a scientific picture or a model that we create to explain something. You know, sometimes we can, most of the time we try to use our writing to explain things. But nice thing about physics, I can draw pictures and explain using those pictures. So that's make my life easier for me. But in lab classes, I have seen like most students just like to write in a lengthy sentences. But for me, I like to put bullet points and draw a picture. If I want to explain a diagram or a scenario that's scientifically happening, okay, that can't be done in every subject, but in most subjects we can do it. So these representations are important. So because of my field, I feel like I can use this both in astronomy and physics. However, we like you to learn like different representation or different explanation of things, right? Anyway, you're taking a physics class, so it's good to know. And if you're planning to be a medical major, then you will be taking 200 level classes in the future. So this will make you a background. So you will get a good benefit of learning these things. Okay. Now we go back to the question, very similar question that we did last time. So if you remember in the exams, you saw identical questions that's very similar to homework questions, but they're quite not, because there's at least a word or a couple of words are different from homework, right? So you can get easily tricked by similar type questions, but they're not similar. They're not 100% identical. So this is one of that type. In the previous class, we used a different representation, but it looks like this one. We had crosses on the top and dots on the bottom, as I remember. Now, this is a different one. Anyway, so look at the picture and think about the direction that the magnetic field lines comes in, and then think about a direction of magnetic field around a current carrying wire. So if you can't remember, you may think about this. I don't know, I found a bunch of pieces around the house that I can use as models. So I believe you can see it. So let's say this is a wire that current flow through. So let's say current is going this way. Okay. I will wait until you answer, then I will go explain this. Okay, let's look at your responses here. Okay. Oh, nice. So 80% or yeah, about 80% know the answer. That's great. All right. So, but however, I like to give a little explanation here. So please try to see my video. So you can select the speaker's view where you can see me. Okay, it's coming from your settings. Okay, so make sure that you see my video. So because I'm trying to do a little demo here. So let's say this is a current carrying wire. So you will say it is a tube, but I picked this so you can easily see it. So here's a current carrying wire. So wires are usually looks like this. Okay, I'm talking about a bare wire. That means a naked wire, that if you remove this cover, the plastic cover, you will see a iron or a copper wire inside, right? So I'm talking about this type of wires, but for easy visualization, I'm using this. So let's say the current is going this way. Okay, so current flows in this direction. I know when you are seeing my video from there, it's mirror images. So you might get confused, but you may take a pen or something like in this shape and think about the directions. Okay, so here's a current carrying wire, and it's the, let's say current is going this way. So the magnetic field line direction, you can find it out using your right hand. So the thumb is along the wire in the direction of current. So I imagine that the current is going this way. For me, it's to the right. So current is going this way, and I see that the top of the wire, I'm looking from this side. So for me, I see like from this side, the top of the wire, the field lines comes towards me. So it's like an arrow coming towards me. So that will be a dot representation. So like very similar to this picture. So on the top of the wire, I see the field lines comes towards me. Okay, and from the bottom, like it's going around and curve around and coming down from here to away from me. When you're looking at the screen, it's like coming towards you, but I'm looking from this perspective. So I see that the field lines goes away from me from this bottom. So it is a cross, right? So you can always imagine that the field lines around the wire is a circle. So these are concentric circles where the wire is in the middle of the circle. Okay. I know it is a little bit hard to see, but think about like a circle. Here's a circle and the wire is in the middle. Okay. So the field lines curve around the wire like this. Okay. So this is a three-dimensional view. So you need to imagine, or you need to try it with the resources that you have around. So here's the wire in the middle. So the current flow through and the field lines are around the wire in these circles. Is it in a one circle? No, it's not. There will be many circles around the wire. So there's a field lines around the wire in a circular pattern, right? So the directions depend on, like, it is a circle. So when you're looking from the top of the wire, it's going towards me, and on the bottom, it goes away from me. Okay, so I want you to use something that can represent wire and circular loops like this, and you may think about it. You can even draw on your piece of paper and think about it. So this is nice that you answered, like most of you got it, so that's great.
So how do you know which way the current is flowing?
Okay.
Like if it doesn't tell you in the question, how do we do it?
Okay, that's a good question. So here's a wire, and I'm looking from this side, and I see this on the top, it's coming towards me, and the bottom, it's going down. So when I keep my right hand, I keep this way. For me, like if I keep this way, so you need to think from your perspective, okay? So make sure you look from your eye view. So for me, I see like if something going in from so let's say, you know, like your right hand rule. So the thumb is always points in the direction of current. Okay, so there are two options. The current can be to the right or to the left. Okay, for a second, let's guess that current is going towards left. Okay, so what I do is I'll keep my thumb along the direction of current. So I assume that the current going towards left. So my thumb goes along the wire towards left. Now I see my four fingers. It's curving around the wire like this way. So that's the field direction. So when I see from my side, on the bottom, it's coming towards me, and from the top, it's go into the page, away from me. So here it will be crosses, down here it will be dots.
Oh, okay. So it just depends on what side the X's are and what side the dots are.
Yes.
Okay.
Here you can easy yourself by thinking there's only two possibilities. One is to the right, other one is to the left. So let's try to the right and see what is the direction of magnetic field. So it is dots on top or crosses on the bottom. So that will be the procedure to do. Okay, so I like to move on. So if you have questions and if you're confused, you may stay after the class. Or you can come a little early next time. Okay. Again, a little challenging question, but you need to think. So there are two current carrying wires, and it's asking what's the magnetic field at the point P. I'm not sure whether you can see the picture from your side. Can you? If not, here.
Yes.
Okay, nice. So there are two wires, and in the middle, it's that's the place that we are looking for the magnetic field strength. Not like in chemistry class or other classes. Here you have to use your hand and rotate it around or draw something and think about it. You cannot just watch the picture and answer it, okay? So you have to visualize. So put yourself, like, imagine that this is how the current flow and what is the direction. So you have to think step by step. All right, so let's see what someone chat. the dot is like the archway. No, here dot means location. So it's represent a location. If it is an archway representation, then there will be a circle around this point. Okay. So this is asking like there's a current carrying wire over here. And there's another current carrying wire over here. So two current carrying wires parallel to each other and they're taking the same amount of current. So let's say 5 amp each. So that's what it represents by II. So the equal amount of current going through the wires. And here, this is a location. So what is the magnetic field strength at this location? All right, so let's look at your responses. Sorry. Okay, it is 0. So that's great. Okay, so let's look at why and how. I know those who answered B and C might be very disappointed. Don't worry, it's a new question. So that's some other things to think about. Okay, so I'm taking you to the my drawing and then share screen. I need the whiteboard. Can I paste something here? Okay, so in the problem, there were 2 wires. So there's a wire on the top and also another wire in the middle. Okay. All right. Now, this is what we should think. Now it's asking a magnetic field strength somewhere in some type of this location, right? So at the center. I'm looking for the magnetic field at this point, exactly at the middle of the wires. Okay. All right. So now let's think about the magnetic field created by these wires. So you know, like it's taking a current of the same amount of current in both wires. So let's say it's taking current I. Okay. So it's current I. You know, we can use 5 amps each, or 10 amps, 10 amp each. Here we are using just a symbol like current I. So we are using the same symbol for both wires to say that it's taking the same amount current. It can be 100 amp each or 10 amp each. It really doesn't matter. Now, what we have to know is what is the direction of magnetic field around this wire. So let's think about the top wire. So the current is going in this direction. So the magnetic field lines are curving around it. So on top, what is the direction of magnetic field? So it's here, and I'm looking at from my side, it's the current is going this way. So it's coming towards me on the top, right? So on the top over here, the magnetic field is coming towards me. So my drawing will be a arch ray that comes towards me. I mean arrow, okay? So like that. Do you agree? Now in the bottom, what happens? So for a second, I forgot about the second wire. I'm just thinking about the top wire over here. I'm thinking about the magnetic field around the top wire. So here it comes towards me, and from the bottom it's go into the page, right? So it will be a cross. Right? All right, now let's think about this wire. So on the bottom wire, again, current is going that way. So on the top, I see a magnetic field comes out of the page towards me, I mean, out of the screen towards me. So it will be a dot representation, right? Like this one. So over here, it will be a dot. Okay. And on the bottom, now the wire current is going this way. Where's my wire? So current is going this way. So on the top, it's coming towards me, and on the bottom, it's going away from me. So on the bottom, it will be a cross. I believe almost all of you can draw this one, right? So marking the magnetic field around the wire. All right, now think about this region. So this location is in equal distance to the wire. So in the middle, from the top wire, the magnetic field is coming out of the page. From the bottom wire, the magnetic field is going into the page. So two things are crossing each other, right? One is towards into the page, one is out of the page. So they are canceling out. So in the middle, it will be zero magnetic field. The distance from here, this point over here is equal distance from the two wires, right? At the center point between the wires. So here, from the top wire, magnetic field is coming out of the page. From the bottom wire, the magnetic field, from the top wire, magnetic field is going into the page. From the bottom wire, magnetic field is coming out of the page. So, and they are equal amount because it's in equal distance to the wires, and the wires are taking the same amount of current. So the magnetic field will cancel out, and over here, the magnetic field strength will be zero. This is a really important concept in a lot of applications. So whenever we want to separate charges, we can use this concept. So if you are taking any chemistry classes, mass chromatometry, so they are separating the charges according to their masses, that's uses the magnetic field strength. And also X-ray scan, not X-ray, it's I can't remember the scanner name. It's okay, I can't remember. I have it listed on the application. So at that time, I'll talk to you about that. Okay, so let's see. Someone send me a chat. So let's see what you say. Okay, so I will summarize this. Here on the top wire, the current is going towards the right direction. So around the wire, if you think about the magnetic field around the wire, those are circles that are circulating the wire around here. So on the top of the wire, I see the magnetic field is coming out of the page. Over here, I see the magnetic field is going into the page because it's circulating around the wire. Same thing happened over here. When you're looking at the center, the magnetic field strength cancel out because they are in opposite directions. So one is coming out of the page, one is going into the page. So they are in two different directions, equal sizes, so they subtract. I will add a couple of similar questions onto the homework that you can try your understanding again. Okay, the last question for the day. It's almost 10:30. Have you ever heard about this? I think all of you have a credit card, right? So in a credit card, maybe you can just try looking at a credit card. So in a credit card, you see like there's a stripe over here with a magnet stripe. This is a magnetic stripe. So depending on your credit card number, the pattern inside is different. Now, when you are using a credit card reader, these days we just clip it, but previously we were like taking it and wipe it, right? Sweep it. So that's mean you're changing the magnetic field in there. So that will induce a current in the circuit. So the card reader can read the credit card number. So depending on your credit card number, the pattern in the magnetic strip is different. So you have your own individual pattern in there. All right, so let's see, what do you think about this? that's right. I think I didn't pick the correct answer. So yes, so it is not recommended to place a credit card with a magnetic strips near permanent magnet. Yeah, you're not recommended to use a permanent magnet around the credit card or your smartphone, because when you are using a magnet around it, when you move the magnet, it can induce currents, and that will destroy the device. All right, so this is the topic that we are moving on to. So the inducing current by changing magnetic fields. Okay, so that's our next topic. We still have about 15 minutes, so I would like to move on. However, I need to take your attendance. So let me take your attendance here. Yeah, please send me your attendance code. All right, so I wanted to make an announcement about the exams. So next exam, it will be open book, open windows, whatever, it will be open resource exam. So you can access anything and there's no requirements to have in your computer or the browser. But for the next exams, you need to have the lockdown browser. So those who have Chromebooks, you can't use that option. So in that case, you need to let me know before the exam and I'll be available on the Zoom. However, when you come to the Zoom, you need to keep your video camera on. Okay, so that's the university requirements. Whether you like it or not, we have to record when you are taking the exam. It is on a procedure. So if you have trouble using the lockdown browser last time, try to have everything available for you. So you can talk to the VCU IT support and get their support and get the directions and make sure you have everything ready for next exams. So I'm not talking about the second mid exam, but I'm talking about the other upcoming exams. For sure, for the final exam, you really require to have the lockdown browser. And I know a couple of you didn't have an ID, the VCU ID. So if there's any way that you can collect or get it shipped to your houses, that's excellent. So please try to get your IDs. So start now. So make yourself ready for use the lockdown browser for exam. So final exam it's required and I need to record it and I have to send a report to the university. So make sure you have those lockdown browser available for you. If you're using Chromebooks, you let me know and you have to join to the Zoom meeting and keep your video camera on. Last time I had a bunch of students taking the class, taking the exam in the having Zoom open, but you didn't have the camera on. But it's fine, it's the first exam. But for starting from the not the next exam, but the following exams, we need to have that feature. All right, so I think all of you have sent the attendance code, I guess. Let's see. Yeah, this time in the exam, I didn't ask you to scan the ID because about 5 or 6 students didn't have an ID. So in that case, I had to bring them to the Zoom link and I cannot handle 20 students in the Zoom. So that's why I didn't ask for a ID scan.
Did you say we need an ID for the lockdown browser?
It's yes.
Okay, because I don't have my VCU ID.
Yeah, that's what I meant. Like, can you try getting it somehow?
Yeah, we have to pick it up from campus. Like they can't ship it to us anymore. So that's been my problem, is just having the time to get to campus.
Okay, so for now, just for this, don't come to the campus. I will contact the people and see like what are the other options for those who doesn't have ID.
Okay.
Yeah, if you don't have an ID, just can you type your name on the chat? So I will keep it as a record.
Professor,
Yes,
when you say ID, do you mean your V number
VCU.
or your VCU card?
Yeah, VCU ID card. So when you're starting the exam, it will ask you to just hold the ID in front of the camera and
Okay.
scan it. So
Okay, thank you.
it's similar to this. All right, so I'll stop counting the attendance. Yeah, if you don't have a VCU ID, type your name on the chat. So I will save it and I will contact someone. I don't know who to contact, but I will at least contact my department head and get some idea like what to do. All right, so I'll finish counting the attendance. 10:30, okay. So at least let's try a couple of things here. Let's learn about magnetic flux. All right, now you can easily get confused with magnetic field and flux. So remember, it's two different things. So we learn about magnetic fields. So you know, like magnetic field line starts from North Pole and it goes towards South Pole. So when you have a couple of or bunch of magnets, then it will give a resultant effect of magnetic field. Excuse me. So this is our new topic is magnetic flux. So magnetic flux is a measure of the strength of the magnetic field multiplied by the area that is it's covering over. Okay, so it's basically the amount of flow of magnetic field through an area. Okay, so what's that mean? So here, as in this picture, these arrows represent the magnetic field lines. Okay, so I don't know what is the source of creating these magnetic field lines. There should be some magnet somewhere here creating these magnetic field lines, right? Now, these arrows represent the magnetic field lines, and now here there's a loop, so that is the area. So if you can measure the magnetic field strength that passing through this area, that is the magnetic flux. So basically, when you calculate in the magnetic flux, you need to know the magnetic field strength, which is measured in Tesla, then time it by the area of this loop or the cross-section area of the place that you are encountering, and then multiply it by cosine theta. Oh, what's that? Cos theta. So if you remember your trigonometry from your middle school or high school, like cos Sokotowa, remember? So Sokotowa, from there cos, C-O-S, cos theta, that's the angle. So this angle means how much angle this loop to the magnetic field. Now here, you can easily see it from this picture. So here, magnetic field lines represented by these red arrows. So they're going down. And here's the area. That's the area that I'm thinking of. So the angle between the magnetic field lines and the area is 0. Okay. Now you can use your calculator and try cos 0. Make sure you have the calculator in degrees mode. So you can use your smartphone and get a calculator. Okay. So here's the calculator, and if you tilt it, you get the scientific calculator. Right? You can even use the computer calculator, and you should be able to see the scientific calculator. Now here, you check the on this side, the bottom right-hand corner, that's the angle mode. So do you see rad or dig? So if you click on this one, it will read DEG, that's degrees. If you click again, it will be RAD. Okay, so this should be in degrees mode if you're using this equation. So now type 60, 60, and then try cos, C-O-S, okay, cos. So I get 0.5. Okay. So if you are in degree mode on your calculator, then cos 60 should be half, which is 0.5. Okay, now try cos 0. So I cancel and I type 0 and try cos 0. It's 1.
What does the B stand for again?
B is the magnetic field. Remember, like measure it in T, Tesla. Okay, I'm going with the theta angle here. So cos theta. If cos 0, like if the theta angle is 0, the cos 0 is 1. Cos 90 is 0. So you can use your calculator to check those numbers. So if you try 90 and cos value, then it is 0. Okay. So here, as you see in these 3 pictures, this area, the black color region, the rectangle, it is the area that represents. So it has different angles with the magnetic field lines. Okay. So again, these red arrows represent the magnetic field lines. Now look at this one. So the area that I'm clearing, the black color area, is parallel with the magnetic field lines. So the angle is 90 degrees. So the flux on this picture is 0 because it is not crossing the magnetic field lines. It's just go along the magnetic field lines. So the magnetic flux is 0. Okay. So cos theta means the angle between the area and the field lines. A is the area, cross-sectional area of the region that this, on this picture, this rectangular black color shade, on this picture, this loop. Then B means the magnetic field strength. Remember, that's what we learned last class, that measured in Tesla. And look at this symbol. What is that? It's like a 0 and an I on top of it. This is a Greek letter pi. Okay, so that's represent the flux. So in any textbook, physics textbook, or any article about magnetic flux, anywhere we are using this symbol. So it is a guaranteed symbol to represent magnetic flux. And this B represents the magnetic. So flux B, magnetic flux, that's what it represents here. Okay. This is a picture of Tesla. So that's in what do you call this, like cash, right? So this is a Tesla in a bill. Okay, I had real one of this. I don't know where it is. I think it is in my album, but this is available. Like Tesla is a very famous guy and he's in all the pictures. All right, so the symbol for magnetic flux is this symbol. And the unit to measure magnetic flux is Weber. That's WB, uppercase W and lowercase b. Weber, we use Weber to measure the magnetic flux. All right, I think that's enough for today. Our brain hurts. We thought a lot. Okay, that's why we say physics is